Hello and welcome to Unit 2 on derivatives and our very first lesson, Lesson 10 on Introduction to Derivatives. Today's learning goal is to be able to define what a derivative is, especially defining it as a limit of a difference quotient and also interpreting it as an instantaneous rate of change. So, just to give you an example first, imagine a driver who's speeding down a highway at 150 kilometers per hour. He's pulled over when he hears sirens, and when the police asks him about his speed, he claims that I've been traveling for 200 kilometers now, or 2 hours, and so my average speed is actually 100 kilometers per hour, which is within the speeding limit. But as I'm sure you know from real context, the police will say, nope, you're still getting a ticket, and your speed in this moment that I saw you was 150 kilometers per hour. And so police officers actually charge you based on your instantaneous speed and not your average speed. So your speed at any given moment. And that's exactly what a derivative is. It's the instantaneous rate of change. So given a function, we're thinking how much our output is changing when the input is slightly changing. So before we get into what derivatives are, just some derivative prerequisite skills here. Please make sure first you're comfortable with exponent laws. So, how to simplify any of these expressions. Soon, when we start working with more complex functions, we are going to have to simplify our expressions. So, it's really important to know these. I've included a video for you as well on Google Classroom. So, please familiarize yourself with that, especially now you've seen limit laws, and soon we're going to see derivative laws. So, please make sure you know the difference between these and how to work with each of them. Next is the equation of a line. So you've already seen, sometimes you might be asked to find the equation of the tangent at a specific point. So it's important to know that given the slope and the specific point, how you can find the equation of a line. Pretty much you just have to solve for b, the y-intercept, and be able to write your equation as y equals mx plus b. Next is just simplifying expressions. So partially that has to do with exponent laws, but also just knowing when you're multiplying to do distributive property, as well as when to simplify expressions. Again, because we're going to be working with more complex functions, so it's important to be able to simplify them using different algebraic tools. And finally, are factor theorems. So sometimes you'll be given these functions and it's helpful to factor them in the limit to be able to simplify. So please make sure you know these all follow specific rules, what that rule would be. And of course, one that's not included there, just thought it was pretty self-explanatory, is our difference of squares, which will be a plus b times a minus b. So please make sure you can complete all of these before you start the lesson. And if you have any questions, please reach out prior to getting into derivatives. So starting with our first example now, where we're looking at the slope of a tangent of a quadratic. So here you're asked to find the slope of a tangent at a point x f of x for the function f of x is equal to x squared, which is our parent function of the quadratic. So from lesson 3, recall that the slope of the tangent of to the graph f of x at a specific point, so the point, for example, here, a, f of a, is given by, remember, m is just our slope notation, the limit of the change of x approaching 0 of the change of y over the change of x. And this can also be written as the limit of h approaches 0 of f of a plus h minus f of a over h. And that was just us looking at our x values getting slowly closer to a specific point, so here being a, and how the output is changing. So again, that instantaneous rate of change at the point a, f of a, and how we find that is by picking points closer and closer with the x values getting closer and closer to a, and we see how much the output value is changing. And this limit also has to exist. So considering our limit rules, we have to be able to find a solution here. Now, the slope of the tangent for a point x f of x for the quadratic function can now be written as m limit of h approaches 0. And here I'm just writing, this is just f of um, x plus h and minus f of x. And because we have our quadratic function, this is just x plus h squared minus x squared. And if you expand this to get x squared plus 2hx plus h squared, we can now simplify by factoring out, well, these two first simplify out, and then we're left with h times 2x plus h. And considering we had that h approaches 0, initially here, this function is not defined because our denominator would be 0. So our goal was to find an expression where we can factor this h out and be able to simplify with the h in the denominator, which is exactly what we've done. So we are left with the limit as h approaches 0 of 2x plus h. And this is just equal to 2x by substitution because here it is defined for h equals 0 and we're left with 2x. So now if I ask you what's the slope of a tangent at any of these x values, you'll be able to tell me here it is m equals 2 1 times 1, so 2x, this is equal to 2. Here, m is equal to 2, negative 1, and negative 2. Here, m is equal to 2 times 2 is 4. And finally, m is equal to 2 times 3 is 6. And now you have the slope of the tangent at any of these points. So if I ask you to find the equation of the tangent at any of these points, all you have to do is remember that this is the point 1, 1, this is the point negative 1, 1, and this just comes from x squared, right? Because that's our output. Here we have 2, 4, and 3, 9. So you have a point, you have its slope, so you should be able to find the equation of the tangent given the point and the slope for any of these. And now, does the slope of the tangent of the quadratic function exist for all values of x? So to consider that, first we have to consider the function itself. So f of x is equal to x squared. And we know here that the domain of this function is the set of real numbers. So x is in the set of real numbers. So any x value we pick, this function is defined. And now similarly, for m is 2x, this is now a linear line. We can also say that the domain is x in the set of real numbers and no restrictions. So yes, the slope of the tangent of the quadratic function does exist for all values of x. And now if I asked you the slope at x equals 324, you'll be able to tell me this is 648. And you have the point, which would be 324 and 324 squared there as your point. And you have the slope, so you will be able to find the equation of the tangent there. Now we're getting introduced to our derivative function, which is that limit we just saw. So the limit as h approaches 0 of now at a specific point. So f of a plus h minus f of a over h. And this has the following interpretations. So we can say that this is the rate of change of y equals f of x at the point p, which is a and f of a for any given function. It doesn't have to be our quadratic function anymore. Any function f of x. And we can also think of this as the slope of the tangent to the curve y equals f of x with respect to x at a. Or finally, we can define it as the derivative of y equals f of x with respect to x at x is equal to a. And one thing I want to highlight here, which is very important, is that with respect to x. The reason for that is our input value is x. If you had the function f of t, it would have to be with respect to t. So this would be with respect to t. and then it would be at the point, um, for this one, it would be P of T, or, well, no, we would still be picking, or it would be T is A, and your point would still be the same. Okay, so please make sure you're watching out for what your input variable actually is. And now, generalizing that, so these were for a specific point, a f of a, but now we want to generalize it. So we say the derivative of a function f of x is denoted f prime of x, so it's read as f prime at x, and it's defined by f prime of x at x and limit of h approaches 0 of f of now x plus h, because we don't have that a anymore, so it's now changed to x plus h minus f of x over h. And again, provided that this limit exists. Now we have two different notations for the derivative function. So first is Lagrange notation, and this is shown by exactly what we just saw, that prime notation. So we say f prime at x, or if you're looking at y, we say y prime. So you might see it written as uh, f of prime of x. Sorry, let me rewrite that. F of prime of x is equal to y prime, and this was that m, the slope of the tangent. We also have the Leibniz notation, which is shown as such, and it's read dy by dx. So we can also now write this one as dy by dx. And same thing as I mentioned up there, this is only because our input function is, or our input variable is x, and we're given the function f of x. But if we had f of t, then we would have f prime of t. This could still be y prime, and we would have dy by dt. So again, that input variable there is important. You might have also had the function, for example, speed, which is shown by s, and this one we would have s prime, and this would be ds over dt. So how your input and output are defined really matters when it comes to the notation of the derivative. You have to make sure you're following the same variables in order to have correct notation. So in this course, we mostly work with y and x, so those are the ones you're going to see most often, but please be comfortable with other variables, and between these two notations, please make sure you're comfortable with both Lagrange and Leibniz notation because they will be used interchangeably, so you have to be able to know that they both mean the same thing. Now we're going to be talking about a concept of differentiability, and we actually are going to come back to this concept later on to see what it looks like algebraically, but for now I just wanted to show you what it looks like with some graphs. So we say a function f of x is differentiable at x is a if f prime of a exists. So if that derivative at that point exists. And at points where the f is not differentiable, we say that the derivative does not exist, and that can be sometimes shown by the notation dne. So remember, it does not exist. And now I want you to think, when might we say that the derivative does not exist? So consider the definition of the derivative with respect to that limit we saw, and when might we say the derivative does not exist? So for sure, when that limit itself does not exist, then the derivative does not exist. But for example, I'll give you one example here. So let's say f prime of x is given by -1 x squared. And we're actually going to see the function for which the function which has this derivative soon. But as you can see, this function or this derivative is not defined at x equals 0. So then we might say the function is not differentiable at x is 0 because f prime of 0 does not exist, right? We cannot have -1 over 0. And now knowing this, I want you to consider what other functions or what other derivative functions or limits might we have where we might not have differentiability? Now let's look at what that looks like on a graph. So first, let's just read the definition here. We say a function is differentiable at a point if its graph is smooth, continuous, and has a well-defined non-vertical tangent line. So vertical tangent line would be just a straight line like that. And if you remember continuity or for a function to be continuous, it means that I can draw that function without lifting my pencil, whatever shape that may look like. So consider these four graphs here. And first, let's just look at continuity itself. This one is clearly continuous. This one is continuous. This one is not continuous. And this one is also continuous. However, all of these four functions do not have or have a point that is not differentiable. And it is that point A. So over here, you see that A. And at this one, it's actually this point here, the origin point. So in the example of the cusp, we have a vertical tangent line, or here we have a vertical tangent line. So, or this one we have a vertical tangent. This one is not differentiable. Same with here, it's not continuous, so we have to lift our pencil up there, so it's also not differentiable. And for these two, the cusp and the corner, it is not a smooth graph because we have a corner or we have the cusp. So in these four graphs, we say that the function is not differentiable at x is equal to a. And again, keep in mind here, a is just 0. Now, a question for you. Can a function be continuous at a point but not differentiable? What do you think? So from lesson 8, and if you don't remember, just click on there and you'll be guided to lesson 8, but I've included the definition here for you. Continuity is defined as, so we say a function f of x is continuous at x is equal to a if f of a itself is defined, so a is in the domain of the function, and it has an output, and if the limit as x approaches a of f of x is actually equal to that point, f of a. So we saw, for example, that was not the case for functions with holes, where f of a is defined, but the limit as x approaches a is not equal to f of a. So then it's not continuous, exactly like this example here. So looking at connecting now this idea to those graphs, yes, you can have functions that are continuous at a point but not differentiable. So consider, for example, the cusp, the vertical tangent, and the corner. Clearly, I can draw all of these without lifting my pencil, so they're all continuous functions, but they don't have differentiability at those specific points. Now, for our final example for this lesson, we're going to use that definition of the derivative with limits to find the derivative of this specific function at a specific point. So our function is f of x is -1 over square root of x minus 2, and we're looking at the point x is equal to 3. So with our notation, and one error here, I'll fix this for you, this should be 3. We set f prime, and now because I have my specific point, this is the same as that f prime of a, right? Where now a is just 3. So f prime at 3, and this is equal to, now the Leibniz notation, d of, so this one I forgot to mention up there, but you can also write the f of x here, but here, because we have that a, so it would be d of f of a by d of x. So f of 3 by d of x, and using that limit definition, this is the limit as h approaches 0 of f3 plus h minus f of 3. So because this is a rational function and has that square root in there as well, it's a bit complicated, so I'm taking it step by step. I'm first just going to find my numerator, and then I'm going to try to substitute it back into this limit. So considering first f of 3 plus h, I'm just substituting it for my into the function to get negative 1 over square root of 3 plus h minus 2. And that 3 and minus 2 become just 1. So this is just negative 1 over square root of 1 plus h. And my f of 3 now is just in the denominator, we have square root of 3 minus 2, which is just 1. So I'm just left with negative 1. So putting these two together, the numerator is now this minus negative 1. So that's why I have a plus 1 there. And finding a common denominator, I have negative 1 plus square root of 1 plus h in my numerator. And you can see already that's something I have to rationalize. So we have to rationalize the numerator here. So we find the conjugate, and again, remember, conjugate is just the first term and the second term. And here, because they're being added, you're just going to make them now subtract. So keeping that negative 1 and keeping that square root, just now we have negative, and this itself is equal to 1. So I'm not changing my expression, I'm just trying to write it in a different form. So in my numerator, I now have 1 minus 1 plus h. We got rid of the square root. And in my denominator, I have the two denominators multiplied now. And in our numerator, we are simplifying that to just negative h and just keep the denominator as is. We don't really need to expand it. It's too complicated and it's not even necessary for the task of finding the limit. So now substituting back into that limit value or the limit expression, we have f prime of 3. This is just that limit we had. So now I'm writing my numerator, which is here, and that denominator is actually just 1 over h. So this is just the numerator times 1 over h. And now these two h's cancel each other out. And I'm left with negative 1. And that's what I wanted to begin with because it was this h in my denominator that was making the limit undefined. So I wanted to be able to rewrite my function or my expression in a way that would let me simplify that h out, and that's exactly what we did. Now, the limit as h approaches 0, and I just kept my denominator as is, and I can check. 1 plus h would just be 1 for h is 0. So I'm just testing h is 0 here. And same with here. This would be 1. So I would have this is defined, and it is non-zero. So then I can just evaluate by substitution. So here, that's exactly what I've done. We find that, okay, sorry, slight error there, but that should be now through substitution. We substitute h is equal to 0. So then 1 plus 0 is just 1, and then here we get negative 2, and we factor out that negative to cancel those two out, and we're just left with 1 over 2. So then the slope of the tangent is 1 over 2 at the point x, at the point 3, f of 3. And just for an extra challenge, I would encourage you to try to find what this point is and try to find the equation of the tangent to the curve at this specific point. And if you graph both the function, so f of x, and that equation of the tangent, you'll be able to see that it actually is the tangent at that specific point. So that helps a little if you're a visual learner. Now for today, you have some practice questions to practice some of these limits as well as just some definitions of limits. There's a practice set for you on Google Classroom as well as a Gizmos activity. So please check those out. And if you have any questions, please don't hesitate to reach out, and I'll see you all next class.